homework a little bit, please. What degree measurement did I give you to switch? 135 degrees? So we're going to take that 135 degrees and we're going to turn it into pi radians. What kind of answer do we have from people? This turns into 3 pi over 4. Or you call it 3/4 pi, however you want to talk about it. Alright? You should have looked up how to do that, and hopefully you've got some kind of a good idea how to go about doing that. Anybody want to discuss it? Good to go? Thomas, what'd you do?
What I ended up doing was just I took pi over 180.
So you took 135 degrees, and then you used pi over 180?
Yep.
Like that, as a conversion factor? Okay, so your degrees are going to cancel with your degrees. You end up with 135 pi divided by 180, and 135 divided by 180 will reduce down to 3/4. So you end up getting that same answer. Good to go. Okay, so we converted from degrees into pi radians. And then what pi radian measure did I give you?
7 pi over 6
And I'm asking you to bring that back into degrees. So anybody want to volunteer how they did that? What did you get, Jalen?
I got 210 degrees. I kind of did the reverse way of doing that. So I took 7 pi over 6 and multiplied that by 180. So that the pi's canceled out. And I was left with 7 times 180 over 6.
So you multiplied by 180 so that the pi's canceled out, did I hear you say?
over pi.
Over pi.
Yeah.
Okay. 180 what?
Degrees.
Degrees over pi. And pi is in radians, okay? I don't like the looks of that pi. So we can make that like that. So the pi's are actually dividing off this time. And you end up with whatever 7 times 180 degrees divided by 6 is.
It's like, what?
1,000.
Can't 6 go right into that 180?
Yeah.
I mean, let's think a little smarter, work a little less harder, right? 6 goes into 180 how many times? 30. And 7 times 3 is 21. Throw an extra 0 on there. Next thing you know, you have 210, right?
Yeah.
210
Degrees.
degrees. Always units of measurement, okay? I'm going to be a real stickler on trying to make sure you put degrees where they belong all the time. Okay, so we're talking about this pi stuff, and I sent you home looking up stuff about pi, but I've never even told you what pi is. Do you know what pi is?
That depends on what question you're asking for.
So what is pi?
3.1411.
Okay, so that's what pi is approximately equal to. Jalen, do you know what pi is?
From what I remember from this was being told that in this case pi is a variable.
Pi is never a variable. Never, never, never variable. Pi is always equal to the approximate value of like 3.14 or 1.5, blah, 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 whatever it is. Okay? It never changes. So it's not a variable. I know it's represented with a Greek letter, and we often let letters represent variables, but pi is not a variable. Pi is not a variable, E is not a variable, I is not a variable, those things that we save specifically for certain things.
This may be wrong, I don't know.
Maybe you're right.
But I know all this has to do with like the unit circle and like pi is something. I don't know, but
Well, I love the fact that you just said something about a what?
Circle.
A circle, yeah. Byron, you want to add something?
I was just going to say that with the US circle, they convert degrees to radian to points.
Alright, so in a nutshell, I'm just going to put it out here. I'm not going to give you a great, big, huge, long explanation, but I am going to make it as short and succinct as I can, okay? So, I definitely have to start with a circle, and it doesn't matter what size circle I start with. I know you guys like to draw circles. You can draw little baby circles, or you can draw bigger circles, or you can even draw a great big circle. It really doesn't matter. That was good.
Wow.
Alright, so I think I'll go over here and I'll put something in the middle. Something kind of like this, okay? That looks a little lopsided, doesn't it?
Not too bad.
So, if I wanted to be really particular, I could just grab my little circle maker, open it up a little bit, make sure it's tight so I don't lose it, and draw myself a circle. Okay. So in this particular circle, I got my center right here, which is nice. This is known as the what? The radius. I'm going to write it underneath there.
wait, is that how many times
Now you got something going, huh?
how many times
Yeah.
Didn't you say before that pi was the number of times the diameter can wrap around the circle? for it to go completely.
Yeah, because a diameter goes around the circle, is that?
Mhm.
No. Okay, you got your words, but you need to tweak them a little bit. Pi is not the number of times a diameter wraps around a circle.
Is the radius?
Then how many times the radius can go around the circle?
It's the number of times a radius goes around a circle?
No.
No.
So you're close, you're close. You got the idea of something wrapping around a circle, okay? But it's not so much the number of times a diameter wraps around a circle, it's the number of diameters that it takes in order to wrap around the circle just once. Okay, it's not the number of times a diameter goes around the circle. A diameter won't wrap around its circle 3 point something something times. Okay? Alright, but you snagged that idea, which is bringing other ideas coming up. Okay, so let's just hit this real kind of quick a little bit. So if I took this radius, and let's say I had like an aux cord or something that I could measure the radius with, and I could kind of go up over here a little bit, I think one radius would be right around here. One radius would kind of end right around there. Does that look right? And it might be off by a little bit, but I'm just eyeballing it slightly with my eyeballs. Okay, so one radius would go there. By the way, this measurement right here, this is an angle measurement, and it's called 1 radian. So mathematically, that's what a radian is. A radian is the measure of the central angle that it would take to cut off an arc equal in length to the radius of the circle. So even if the circle were bigger, you got this great big circle here, it's still going to go all the way up to about here, where 1 radius is. And therefore this is 1 radian. So a radian is a unit of measurement to measure angles, just like a degree is. Just like inches and feet and miles and yards, they all measure straight line distance, right? And meters and all those things. So a radian is another way that you can measure an angle measurement. This would be like 1 radian. This would be like 1 radian. It doesn't matter how big the circle is, right? Because the angle measure itself is measured down at the vertex. So it doesn't matter how long you extend it to or how big your circle is. A radian measures approximately that big. Now you're going to have another radian, and it's going to bring you over here someplace, okay? This will be 1 radius, and this will be 1 radian down in there.
So that's 2 radian.
And if I did it again, I'd have another radius, or length of a radius wrapping around the circle as part of the arc. And this would be a 3rd, what? Radian. And then I'd have a little bit left over here. And I'm probably not drawing them good enough to scale. I'm not measuring anything, I'm just eyeballing it, like I said to you before. This right here turns out to be a 7th of a radius. So therefore down here is a 7th of a radian. Okay, so how much gets you halfway?
3.1.
About 3 1/7, right? Radians is equal to about half a circle. Does that make sense?
Yeah.
If you put 3 1/7 in your calculator,
You get 5.
you get about 3.14. Now you got to keep going a little bit. And 3 1/7 isn't an exact measurement either. It's an approximation. But that is known as pi. Pi radians, and we just say rads usually. Pi radians is approximately half your circle. And how much is a circle?
360.
360 degrees, most people tell me, okay? And what's half of 360 degrees? 180 degrees. So that's why when you guys were doing those conversion factors, some of you were using pi over 180, and then I think you turned around and said, I just flipped it upside down and used 180 over pi, and my pi is canceled off. You remember that? 180 degrees and pi radians are the same exact thing. And Mark, on your paper, you had the number 1, didn't you? Okay? These are both equal to the number 1, so you can use either one of these conversion factors if you want to go from degrees to radians or from radians to degrees. Just multiply whatever your value you're given by the number 1, and you'll switch measurement. Like for instance, if I had, let's just go for 5 pi over 3. This is in radian measure. I want to switch it to degrees. I want to make the pi disappear. Don't I want a pi on the denominator? So I'll put a pi on the denominator. That means 180 goes on my numerator, 180 degrees. The pies cancel off, 3 goes into 180 how many times? 60 times 5? 300 what? 300 degrees. Pretty simple. And you might get some other people to say, you know what, if I'm taking pi over 3 and I want to get rid of that pi, I'm just going to substitute 180 degrees in place of pi because I know they're the same. And 3 goes into 180 how many times?
60.
And 5 times 60? That's pretty fast too. So as long as you understand that 180 degrees and pi radians mean the same basic amount, then you're good to go. Now it'll bring you to your unit circle. And if you're on your unit circle, let's pretend this is your unit circle. Some of you know about the unit circle and some of you
No.
don't know about it. But this is 0 and this is pi. Right? Do you know what's pi?
1 half is pi.
What is it?
1 half pi.
1/2 pi or pi over 2. Somebody down here, do you know this one?
3/4 pi.
3/4?
3/2 pi.
3 over 2 pi. Okay, so if you don't know it yet, you will soon, okay? This is 1/2 a pi. This is another 1/2, which makes a whole. This is another 1/2, which makes it 1.5, or 3 over 2. And when you come all the way back over here, you get what? A whole circle, which is 2 pi. And that makes sense. I hope it makes sense, because pi is supposed to be about 180 degrees. Pi radians represents 180 degrees, so 2 pi would represent 360, which is what you get going all the way around. Okay. I'm going to do something now on the board. It's going to be a lot of drawing. But now that you understand the pi business, it should be a little bit better. Let's see. Change of plans slightly. Instead of me doing that particular thing next, can I just review with you quick what we did on Monday? What did we do Monday? Please be able to tell me what we did Monday.
We took notes on 6 dollars.
We did sine, cosine,
Yeah.
tangent, cotangent, secant, cosecant. We also did one special triangle. Which one was it? Yeah, that 30, 60, 90. You take that equilateral triangle. I know you remember the word equilateral. Take that equilateral triangle, chop it in half, and you end up with a 30, 60, 90 triangle. So just to bring that back up, and I said, what is a very nice number to put on each of the sides, knowing in advance that you're going to cut them each in half. What number? Was it? Say it again? 2. With a 2, right? Put a 2 on each of these, and you chop this in half. And then you chop that in half, the 60 gets split into 30, 30, so I'm going to draw only half of it now. So this is 30, this is 60 degrees. That has to be 90, because 30 and 60 make 90. And to get 180, the other one has to be 90 also. Okay. This is a 2 right here. How much is that? It's right there. Has to be a 1. And then I put that quote on the board. Remember the quote that said in a 30, 60, 90 triangle, the side opposite the 30-degree angle is always half the hypotenuse. Okay. Do the Pythagorean theorem, and what are you left with right here? Square root of 3. So every single 30, 60, 90 triangle has sides that are in the ratio 1 to 2 to the square root of 3. Which of these is the biggest? The 2 is the biggest. Okay? Remember, the 2 is the biggest. 2 is larger than the square root of 3. True? You okay with that? All right, I hope so. All right, the other triangle that I wanted to do with you today is the other most important one as well. It doesn't come from taking an equilateral triangle and cut it in half. It comes from taking a square and cutting a square in half. So I'm going to take just a square. And what would be good dimensions to put on the side of this square? Side. We don't measure sides with 90 degrees.
2?
1.
Well, in this case, we have 1.
Oh.
Okay? Because I don't need to cut the side in half, do I? When I make triangles out of this by cutting this square in half, I'm not going to go down the middle. That wouldn't give me triangles, it would give me 2 rectangles. I want to go diagonally from corner to corner. So I really don't need to cut any side in half. So if all the sides are the same, the easiest number for me to put down there is 1, 1, 1, 1. But I did cut the angles in half, didn't I, when I did that? So how many degrees are in each part here? 45 in each one. 45 here, 45 here, and 45 here. So I only really want one of those triangles, okay? I'll draw this one. 45, 45, 1, 1. So not only is it a right triangle, but it's an isosceles right triangle. The two legs are equal. And you can turn this around if you felt like it and draw it the other way. 1, 1, 45 here, 45 here. What's the hypotenuse going to be? Do the Pythagorean theorem in your head and get the hypotenuse. Square root of 2 is good. So the ratio of a 45, 45, 90 triangle is a 1 and a 1 and a root 2 on the sides. Which of these numbers is biggest? The 1, or the root 2?
Apparently the root two. Wait, no, you did root two.
Root 2 is bigger.
It's the hypotenuse. It has
It's
to
the
be.
hypotenuse, it has to be, we just drew it. Something I didn't do for you over here, maybe I should have. What number is this, the square root of what number is 1? 1. Square root of what number is 2? 4. Square root of what number is the square root of 3? Square root of 3. Okay? So isn't the square root of 4 the biggest here? So 2 is. Whereas over here, I would call this the square root of 1, the square root of 1, the square root of 2. Square root of 2 is bigger than either. And it's approximately 1.4, I think. So it's a little bigger. Alright. So I just want you to know both of these triangles. We're going to be playing around with both of those triangles quite a bit. And tomorrow's warm-up is going to have some questions about those triangles. Alright. Next thing we're doing. And I'm kind of jumping a little bit, but that's okay. How many special triangles do you know? You know 2 of them. What are they called?
30, 60,
30, 60, 90?
45.
45, 45, 90. Those are your 2 special triangles, right? Okay. So, we are going to sketch angles in standard position. And I'm throwing a whole lot into this lesson, okay? All at once. We are going to sketch angles in standard position. And I'm going to put a few bullets here, okay? Positive angle measures are counterclockwise. Negative angle measures are, guess what? Are clockwise. The vertex is always the origin. What do I mean when I say origin?
Center point. 0, 0.
0, 0, because we're going to graph them, okay? The vertex is always the origin, 0, 0. And the initial side is always the positive x-axis. All right. So I'm going to draw 4 pictures. And when I draw 4 pictures, I'm going to put them on these 4 spaces. So for the picture in the top right, I'm going to be drawing something in quadrant 1. And the picture in the top left, I'm going to go for quadrant 2, quadrant 3, and quadrant 4. And I haven't even discussed with you quadrants yet.
So those are going to be the standard positions for those objects?
Yes. For those angles. So in each one of these little sections, draw yourself an XY axis. We all know where the positive x-axis is, right?
Quadrant 1.
Well, the positive x-axis borders quadrant 1. Here's my origin, and here's the positive x-axis right there. So this is called my initial side of the angle. And we've already discussed what an angle is. An angle is two rays sharing a common endpoint, and that common endpoint becomes the vertex of your angle. And the angle measure itself is how far these two rays get spread open from each other. Okay? You have really big angles, really small angles. We can have really, see, tricky again, ready? Oh, I can. Yes, I can. All the way around to 280 degrees, 360 degrees. Past 270 is what I was thinking. Okay, so if I want to open an angle here in quadrant 1, and I want it to be only within quadrant 1, once I go that far, I'm not in quadrant 1 anymore. Okay, quadrant 1 is everything over here. So this is how many degrees right here? This is 90, so I need to be less than 90. So the angle in quadrant 1 has to be what kind of an angle?
Acute.
It has to be acute. So I'm going to draw an acute angle in quadrant 1 using this as my initial side. I open up someplace, and here is we call this the terminal side. What's terminal mean? Huh? Final. Okay, it's where you end. Alright, so it's your terminal side. Alright, this is my angle itself. And we call that theta. I'm going to put another little bullet over here. And I'm going to put that symbol, I'm going to say theta. Is the angle. Now in quadrant 2, I still need my initial side. So this is still my initial side. That never changes, you guys. The initial side is always on the positive x-axis. But now this angle has to open up bigger than 90. What kind of angle am I going to make? That's obtuse. But it's going to be less than 180. I don't want to go to 180 because then I won't be in quadrant 2. I'll be on the x or y axis. In this case, be the x-axis. So I'm going to open up this angle that has a vertex at 0, 0. I'm going to open it up until it gets all the way over here. And then this will be the other piece of my beautiful angle, like that. All right? And this will be my terminal side, won't it? And I like to draw a little arrow there and mark theta. Can you imagine what it's going to look like in quadrant 3? I hope so. We have an initial side on the positive x-axis. Our vertex is 0, 0. I basically need to open this up until I'm bigger than 180 and all the way past there, right? So I'm going to go from my initial side all the way over into this quadrant. This will be my terminal side. And this is my theta. Now, I don't even know what kind of angle that's called. It's not acute, it's not obtuse, it's above and beyond, I don't even know. And now, the last one, initial side again. Your vertex is 0, 0. You start opening, you go all the way around, almost the whole entire way, right? But you're over here in quadrant, what's this quadrant? 4, okay? And this is called your terminal side again. And this whole thing is your theta. That's pretty simple, isn't it? One more letter to give you. One more letter to give you. And the other letter is called alpha. It is the Greek letter alpha. It looks like the Jesus symbol, you know, the fish that you see on a lot of bumper stickers in the back of people's cars. Okay, so that's your symbol. It is the Greek letter alpha, and alpha is the reference angle formed by the terminal side and the closest x-axis. reference angle formed by the terminal side and the closest x-axis. So now I'm going to go back in each one of those pictures and show you where alpha is. Remember doing this last year?
We didn't do alpha and theta last year.
Didn't do alpha and theta? Okay. Well, come on over here. In quadrant 1, if all you do is come up to this terminal side, then if I want to form the angle from the terminal side to the closest x-axis, won't it just be this angle? So in quadrant 1, alpha and theta are the same thing. In quadrant 2, I'm over here in quadrant 2 now. If I'm on the terminal side anywhere, and I want to compare the terminal side to the closest x-axis, is the closest x-axis going to be the negative x or the positive x? Negative. So in here is my little alpha, okay? Matter of fact, I'll do a little double arc here and say alpha. That's my alpha. Which is way cool. I think it's way cool. So we don't usually use theta when we're in quadrant 2. We just use alpha and we apply some more rules. So we're allowed to always use nice and cute angles, which is cool. Over here, I'm now in quadrant 3. I'm on my terminal side, and I want to form an angle between my terminal side and the closest x-axis. Do you see the alpha? Where's the closest x-axis? Right above it, right here? Did you say positive? No, negative. Good. Okay, right above it. So the angle formed with my terminal side and the negative x-axis is this angle right in here. And this is my alpha. In quadrant 4, alpha is like in your face. See it? Everybody? Between the terminal side and the closest x-axis. Here's your alpha here. Got it? So you throw this all together and you learn a whole lot. This, by the way, this is quadrant 1, 2, 3, and 4. And we have a lot more to build on because now I want to take those 30, 60, 90 triangles and those 45, 45, 90 triangles and I want to put them in standard position all the way around the circle. And then we will build what we call the unit circle. Got it? All right. I'm not a big fan of the unit circle whatsoever. I'm really, really not. I prefer to use my graphs or something else, but yeah, it's okay. We'll learn it anyway, just a little bit. Let me see, one other thing I'll send out here. I guess I'll let it go. I'll be good. No, I just have to. I have to. Check this out. If you're in quadrant 1, your alpha is right there. See it? Notice I connected down from my terminal side to my x-axis. If I'm in quadrant 2, my alpha is right there. You see it? If I'm in quadrant 3, my alpha is right there. And if I'm in quadrant 4, my alpha is right there. Got it? I heard somebody say it. What'd you say?
Bow tie.
Bow tie? Okay, so if you're not playing with one of the pieces of the bow tie, something's wrong. And you never, ever, ever go perpendicular to the y-axis. You always go to the x-axis. Never, ever draw your alpha to the y-axis. Everything is to the closest x-axis all the time. Alrighty. I think I will, how many minutes we got? We got not much. Okay? So I'm going to end that. We'll come back tomorrow. We'll start talking pies and around the unit circle and cutting things up. Okay? Alright? We're good. There's no homework assignment. Anybody learn anything? Tell me, hold on first. Let me shut this off. Tell me what it is you learned.